We are going to look at the process of making a carboxylic acid by preparing first off a nitrile and then hydrolyzing that nitrile to the carboxylic acid. This first step is something that you've done since 351. This is the formation of a nitrile from an alkyl halide. I'm going to use the same one I had previously when you looked at the carboxylation with the Grignard reagent. So in this particular reaction, you are going to have more than one step again. The first step would be the addition of the nitrile group. So you can have any cation you want with it. Oops. But you do need to have CN, and you need to make sure this goes by either an SN1 or an SN2 process. It depends on whether you want a shift to occur or not. I don't want a shift, and this one isn't capable of that anyway, but I'm going to give it SN2 conditions. And then once you would have the nitrile, you would need to convert the nitrile into the carboxylic acid. And this is done with an oxy acid in water. Okay, so to get this reaction to move toward the product, you would have some of this oxy acid in water. These would be the conditions that we would need to get this particular reaction to go. This first step I'm just going to do right down here. It's not a big deal, but you have your cyanide. The sodium is a spectator ion, and this carbon will act as a nucleophile. It will do this backside attack and kick out the bromine. And as that occurs, you've added the nitrile group. And then you've got your bromide as your leaving group that would now pair up with the leftover sodium. And this is what you would get after that first step. It's just an SN2 substitution. The neat thing about that first step is, again, you do make a carbon-carbon bond. So you're able to, again, have a reaction that creates another carbon-carbon bond. That's very important when you're looking at these reactions. You do need to add the carbon. Alright, so now we have our nitrile. And this nitrile reacts very much like a carbonyl carbon would. It is a pseudo-carbonyl carbon. It has pi bonds to an electronegative atom. And that's really the big deal here. It's not an oxygen, it's a nitrogen, but it still has pi bond to an electronegative atom. And you've got protons in solution. You've got an acid. So acids are going to donate protons to an electronegative atom. In this case, that'd be nitrogen. Nitrogen can act as an electron pair donor and pick up this proton from the acid. Now once it picks up that proton, be aware that this has resonance stabilization of that positive charge. This is why this is a favorable thing to do. It's due to the fact that you can break one of those pi bonds, give the electrons back to the nitrogen, and as you do so, carbon picks up that positive charge. Now as you look at these two different resonance structures, be aware that the one on the left, everybody's got an octet. The one on the right, the carbon does not. So the one on the left is the predominant resonance structure because everyone has an octet. Now you can use either one of these two though. It's not a big issue. But water is also present in the solution because you dissolve the acid in water. And now that we've protonated, this has activated the carbonyl carbon, or in this case the pseudo-carbonyl carbon, towards nucleophilic attack. And water is going to act as that nucleophile because it is the electron pair donor. So it can add to the carbon, and as you do so, you can break the pi bond if you're using this resonance structure, or if you want to use the other one, just add it directly. It doesn't matter since they're the same thing technically. Okay, we've got a new intermediate, And what we're going to do now, like we've seen with other tetrahedral intermediates, I know this one's not a tetrahedral, but it's pseudo-tetrahedral, is you're going to do a proton transfer through solvent from the oxygen over to the nitrogen. And again, your solvent in this particular case is water. So we're going to do the proton transfer to the solvent. So the solvent picks up one of those two protons on the oxygen and you give electrons back. And then what we're going to do is the proton transfer from solvent back to this pseudo-tetrahedral intermediate. And this proton can go either to the nitrogen or to the oxygen, since both of them are electronegative, and both of them have lone pair electrons. It doesn't matter which one gets it. But to do something productive, you want to give it to the nitrogen, not the oxygen, though either one could actually do this. So show the nitrogen picking up the proton and giving electrons back to the oxygen here. This will complete the proton transfer through solvent. Oops, wrong color. Now that proton does prefer to be on the nitrogen due to the fact that the nitrogen has the ability to have resonance delocalization of that positive charge. Whereas if it were on the oxygen, there would be no resonance delocalization of the positive charge. So the resonance structure that we have here initially we'll go to the carbonyl carbon, and then we can draw another resonance structure as the oxygen acts as the electron pair donor toward the pseudo carbonyl carbon. This is why it's a good idea to have the proton on the nitrogen. Again, I'm going to go back here in a minute, but if you'd had the proton on the oxygen, like it is here, there is no resonance delocalization of the positive charge. It has nowhere to go. And this is why it's preferable to have that proton on the nitrogen. There is resonance delocalization of that positive charge. Now I'm going to redraw the one on the left and use that one. So be aware there is significant delocalization of that positive charge. Okay, and now this carbon still has a pi bond to an electronegative atom, so it is susceptible to another nucleophilic attack by solvent, since it is still a carbonyl carbon, and as I showed you a moment ago on the other slide, it has significant delocalization of the positive charge. This is very much what we have seen, like with Fischer esterification, once you protonate the carboxylic acid. There are three resonance structures, and it will activate the carbonyl carbon toward nucleophilic attack. So the solvent, the oxygen of it, will add to the carbonyl carbon and break the pi bond to make a protonated tetrahedral intermediate. This is the protonated tetrahedral intermediate that you make. What we do at this point is again another proton transfer through solvent from the protonated oxygen to the nitrogen. And again, our solvent here is water. So proton transfer to solvent, you pick up the proton and you give electrons back to make the tetrahedral intermediate. And now we're going to do the proton transfer from the solvent. And the nitrogen or either of the two oxygens can technically pick up this proton. It doesn't matter which one does it. But to do productive chemistry, give it to the nitrogen. So the nitrogen will act as the electron pair donor to pick up the proton and give electrons back to the oxygen. And what we've done by doing this is created a very good leaving group. So at this point you can take either one of these two OH groups that are attached to the carbonyl carbon and make a pi bond. And as that occurs, carbon can't have 5 bonds, so you break the bond between carbon and nitrogen to kick out ammonia. I think I can fit this over here. And get this species. Now, this protonated species that I've just made, it does have resonance delocalization of its positive charge, so let me take the time to draw all of that. I'll redraw the first structure we had on that other slide. The point is that there are 3 resonance structures showing the delocalization of this positive charge. Now, you can then remove the proton, and it doesn't matter from which oxygen you remove the proton, but you're going to remove the proton with the ammonia that you kicked out previously. And it will act as an electron pair donor to pick up the proton and give electrons back. So that at the end, we're going to have our carboxylic acid. And you'll also have an ammonium. If there is more base, you could remove the proton on the carboxylic acid, but if you added some more acid, you'd reprotonate it. This is how you convert a nitrile to a carboxylic acid. So some considerations here to be aware of. This particular reaction, you would have issue if there were any other carbonyl groups present somewhere else in the molecule, because the proton may protonate that other carbonyl position and then water may add to it. So if you have any other carbonyl groups present somewhere in the molecule, you would need to protect them as an acetal before going through this reaction. And as you add water and that proton, you would deprotect them as well. So it would be very specific for what you want. You would also not have any issue with any acidic protons like an OH, SH, or NH position like you do when you use the Grignard reagent. So if there are acidic positions that you're worried about, this would be the route to go if you're thinking about target molecule synthesis.